ve bu güzel konuşmanın ardından sizleri hepinizin çok yakından tanıdığı Barcelona denince hepimizin de aslında aklına gelen ve tüm dünyanın bitmeyen kilise olarak tanımladığı Antoni Gaudi'nin muhteşem eseri Sagrada Familia'nın tamamlama projesinin yürütücüsü olan Profesör Mark Burry'nin aynı zamanda Antoni Gaudi ve dijital mimarlık üzerine birçok yayını bulunuyor ve Mark Burry'i hepimizin merakla beklediği sunumu. Bir ömrün ötesini tasarlamak, Antoni Gaudi ve Barcelona'nın Sagrada Familia Bazilikası'nın devam eden inşası için oluşturduğu Tasarım Şeması adlı sunumunu yapmak üzere sahneye davet ediyoruz.
Thank you. Thank you for the introduction. Thank you very much for the sponsors for making this visit possible. And I have to say that I had been curious how I would follow from Carlo Ratti, but he's given me an excellent opportunity to segue into the role of Antoni Gaudi in our thinking. And the other challenge, of course, was how do I talk about Gaudi in the future? Well, in fact, it's not that difficult. I've got only half an hour to take you on a very fast pace account of Gaudi and his story on the Sagrada Familia Church. What I intend to do is show you, pick up his life in about 1914, 12 years before he died, when he had the challenge of trying to finish an unfinishable basilica. He had a terrible time with his clients at that point, and he lost all his secular commissions. All he had left was the Sagrada Familia. So just to make sure we know which building we're talking about, this is the state of the building when Gaudi died. This should be sound. That was all he built, just one side and one end of the building. And everything else you see is built after his death in 1926. So he's a Catalan architect. He wasn't the first architect for the project. He inherited it from a former architect who had started the project in 1882. So Gaudi joined it in 1883 and worked through till 1926, when he died aged 74. Now, when you look at this video, you get the sense that this is a building that's being completed. He conceived of the space as one giant forest with these trees and columns and the roof above. And the question, of course, has always been, how can anybody finish the building when somebody like this, producing work like this, is obviously a unique character? Well, I'd love to tell you the whole story, but we haven't got time for that. But what I thought I could do in terms of thinking about the future is just show you very quickly the progress, not just in the building, but in the use of technology, to give you a sense of how an older project can actually give you all the clues you need to feel optimistic about a future that will be more sustainable and perhaps less of a challenge. Here's the powerhouse of decision-making. This is the model workshop. Everything is made here. It's not a building that we draw. On this video here, I can actually show you what the challenge is that remains, because here's the building as it is, and you're seeing it emerging as it will be in 2026, with the sacristies completed, the main tower over the apse, which is the Mary Mother of God tower, the big auditorium that's just nearing completion, that's just over the center. This will be finished at the beginning of next year, that space up there. These towers have already begun construction and will be finished the next few years. The Passion facade also is nearing completion. That'll be finished next year. These baptistries are a little bit further behind, and this is what I'm working on at the moment, which is the Glory facade. It's known as the last great unknown for the project. There are the evangelist towers there, and then finally in the middle, you'll see the main tower for Jesus Christ. So there's a lot to do, I think you'll agree, before 2026. But that is the date that we intend to finish it. That is the centenary of Gaudi's death. So to pick up the story, this is the plan of the building when Gaudi died. He had managed to complete just one transept over here and the wall round here. And then after 43 years, that was it. Since then, these towers of the transepts were finished in 1978. I joined the project in 1979 as a researcher because at that point, the two architect directors, had just begun to think about what would happen with getting the rest of the building completed. And I'd arrived there and asked them two questions, which one was, where was the authority to continue the building if all Gaudi had managed to do in 43 years was this part here, and now we had the rest of it? And anyway, what is the process of communicating to everybody building it? How do they know what their task is? If you're a stonemason, what is your work to do in the morning? And they told me that the answer was a series of models. And the models looked like, somewhere there's a picture, here we are. The models looked like this. They pointed to boxes and boxes and boxes, and they said, did I understand that Gaudi had a system, a schema? And that's what I really wanted to reinforce in this talk, is that this schema, this armature, this scaffold allows others, including myself, to pick up where he left off. The challenge has been even just producing a model. This model is 2 years old. It's the first time we've ever, as a design group, been able to look at the whole of the building, because we didn't even have 3D information of the original group of towers, and yet we had to do the whole of this construction. So it's only in the last 2 years that we've had computers that are powerful enough to collect all the data. We've had scanners that are easy enough to use to make the point cloud so we can measure the building, and we've got the printers that can print this building. So this is a 1 to 200 model made entirely by hand. But what's interesting about this model is nearly everything you're looking at is what's known as a ruled surface, or a doubly ruled surface. It's a geometry, a particular type of geometry. It's not what you'd expect. The sort of Gaudi that we're familiar with is buildings like La Pedrera, which is this building here. This is not a geometry that we're familiar with. This is a free-form surface. You can see even the way artistically he goes from a crease to a fold. It's just not a rational way of describing a building. It's not surprising that the building took 4 times as long to make, cost 4 times as much, and every piece of stone had to be lifted and dropped 4 times to be completed. This was in 1914 that this crisis, when Gaudi found that he had these 3 projects, this one and 2 others, that just left him without a client base. So imagine when he was ill, because he was very ill, he had quite a serious life-threatening disease that took him out of the city to convalesce for several months, that he must have been wondering what he was going to do about it. And what he did about it was go back to his school books and look at surfaces like this one, which is a ruled surface, doubly ruled surface, a surface which is geometrically flexible or plastic, but and doesn't have the rigidity of formal geometry, but on the other hand, doesn't have the looseness of a free form. You can even get images of this. This is a parametric model, a physical model. Parametricism, of course, is the current big thing. Quite a crazy term, really, when we think that parametric models existed. This is this form here, made in a model that can show its infinite states. That's probably not very clear, which is just as well, because I have gone to the trouble of making a video showing how this surface is so plastic. If you take a cylinder, composed of straight lines, and you start moving the bottom hoop in relation to the top one, you can see an infinite variety of surface emerge. If you go too far, you go to the 2 cones, and this way you get the cylinder. So this is what Gaudi's thinking in terms of a three-dimensional non-Euclidean surface, if you want the technical term. Now, the way he put this into action, as you can see, there's that model I've just shown you as an animation is this model in action. Here's the evidence that he understood the value of these surfaces. These are the links. My first bosses were these two gentlemen here. They were 90 when I joined the office in 1979. And here you can see an example of one of these applications of the geometry. This is the clear story window, which is running along the top of the building. And it is everything you're looking at there is a ruled surface, doubly ruled surface. It's either a hyperboloid of revolution, which is the form I've just shown you, hyperbolic paraboloid, or a plane. Those are the three surfaces. That was the primary material. This was my task, was to measure it. But then we had the lineage of the original plaster model makers who could describe how Gaudi had worked with them as a designer. So this is Gaudi's design process using these surfaces. There's a hyperbola here, that's the curve, that's rotating around this pivot. It's making not what you want, but what you don't want in order to produce what you do want, which is one of these surfaces. So that's half a hyperboloid revolution. Here's how they join. You get an intersection between two adjacent surfaces. You then get a point of intersection between three of these lines of intersection. And so the window emerges. This process is a 6-month exercise. To make one window, one version, is 6 months. And my task was to work with one of these directors. I was inspired by thinking back to my own understanding of geography, where you can see triple points in nature, every single hilltop. So what had seemed to me at the beginning a completely improbable and unfamiliar task was actually made real when I realized this was a kind of mapping, not an architectural challenge. So as Carlo was saying, it's these days the problems that we want to address require many disciplines. Well, this project, right from the start, requires many disciplines. You can't just come at this. If Corbusier was standing in the office, as much as he admired these models, and that's on record, he would not have been able to address this project in the way that we've had to. So there's the map. I'm mapping the contours of the surfaces. There are the lines of intersection. There are the triple points. And here are the computer drawings made before the computer ever came into our lives. This is another projection looking at it from underneath. And then, of course, we look at it from the side. And through millions of little calculations, we eventually come to a working methodology by which this window could be made. There you can see the results of Gaudi. So this is the work that Gaudi did in the last 12 years in a nutshell. He then, if you want to see this in action, this is the hyperboloid of revolution taken away from another solid, and you can see the plasticity of his thinking. This is very apparent when we do an animation where we're changing just one or two parameters of the many we can. And if you just keep an eye on that area here, you can see that it's not a simple formula. You need to know exactly what the right stopping point is, as only Gaudi could do. You can see this here. This is the window that I just showed you. Here we are exploring different sets of values, different parameters, in order to eventually find an orange, mathematically correct surface that completely matches that of Gaudi's own design. You can see that's round about this point here. We can get that. Okay, if this is all going too fast, don't worry about it. I'm not really asking you to understand what he was doing. I'm trying to get across the message that what he did was worth understanding. There is a schema to this. It means that people like myself can come afterwards and pick up where he left off. There's also a logic. If you look at the construction process, looking at these surfaces, what you're seeing here is traditional Catalan vaulting being laid against formwork, which I think is a little bit slow. You can just see here that the logic of the straight line makes it relatively easy to make. And that's really the main point, that he's found a system using geometry which gives the stonemason and the bricklayers a relatively easy task in their construction. Here you can see on this little animation here just how powerful Gaudi's conceptual ability is. He's taking 4 of these hyperboloids, hypothetically, and we just put them round a ring, and there you can see this plastic architecture. Depending on what values you give these, the geometry of the that's not there, as it were, you can see exactly how Gaudi is working conceptually. Now, what I want to do is just quickly take you through 3 periods of the project. The first one would be over 20 years ago, when we're looking at the columns. The columns of the building, every single one is slanted to take the loading, and every one has the same formula for its construction. So you can see here, this column, if I ask my students, which I do routinely, can you describe how you would tell the builder what to make? How does the stonemason know what to make? Is this a complicated piece of free-form geometry? And the answer is, of course, that it's not. It couldn't be simpler. And what I will do is try and show you how simple it really is. Gaudi was the ultimate architect. He did everything at first principles, including the structure. So not only did he sort of design the structure of the building to be as efficient as possible, he even personally investigated the strength of materials and tested them, as you can see here, working out which stones would be best used for different parts of the building. His evolution of the design, he originally started looking at the columns as being a simple twisted column. He then looked at what would happen if you take 2 of these columns and intersect them. And the one you can see in the right-hand side is the eventual profile that he selected. The principle for the column is the helicoid. This is a ruled surface, but not a double-ruled surface. A double-ruled surface has 2 lines at least passing every point on the surface, whereas a helicoid is just a rotated a single line. But it's a very powerful surface to evoke for this. And the geometry he decided on was to just take a concave and convex parabola to make a profile, which looks like this. And perhaps it's easier if I show this on animation. Here you can see the profile and its generation. So a convex and a concave parabola, it couldn't be simpler. And there's the profile for the base of the column. But the interesting thing is there's actually 2 profiles. They're both on top of each other. And these 2 profiles counter-rotate in order to define the column at various points in its height. So this is 4-dimensional architecture. It's 3-dimensional in form and 4-dimensional because it's actually using time and displacement to describe itself. So there you can see the column, and I'm going to show you how these lines appear. So as the column goes up, you can see these 2 profiles are just rotating with respect to each other. And when it gets to a point where they're exactly halfway out of phase for each other, they double. So at this point here, if we carried on going, when it stops, it would just go back on itself. But what it does is that they double. So the column is actually an expression of life, in the sense that you've got 2 profiles at the bottom, 4 at the after 8 meters, and then 8 profiles, and finally 16. And if you think this is horribly sort of far too mechanical, then let's have a look at this machine here that the model makers made. There's the profile you can see, and this profile literally rocks backwards and forwards along this rail. So there's a rail to the right and to the left, and the profile can either rock to the left slightly or to the right. And you can see plaster of Paris. Because of my time, I have to do this super fast. It's a bit like watching paint drying otherwise. But just this process takes 20 minutes while the plaster's setting. And as the plaster gets harder, he just goes backwards and forwards with that. So I think you get the idea. It could not be simpler. And what an extraordinary, when you take you back to look at the column itself, what an extraordinary outcome. The process by which they were made at the very beginning of the digital age was to accept that these parabolas could be relatively easily described. So we digitized them. This is in 1992. We digitized the profiles through templates. They then programmed a machine to take blanks of masonry. We'd cut away as much of the stone that we didn't need before it would go to this robot saw. And all this saw could do was just do a curve and then move up 5.5 millimeters. So this is the state-of-the-art 22 years ago. There's the saw cutting away. Each piece took 36 hours to make. There are 8 pieces per drum. Each drum is 1 meter high, and the columns are 14 meters high, and there are many columns. So you can even see with the state-of-the-art technology of 22 years ago, this was a very, very slow process. And there you can see the pieces ready to be put into the project. So if I just move forwards to 1999, and this area here, there was a rose window was required, and the period was exactly 12 months to go from design to the completed window. The reason for this, it was intended to commemorate the beginning of the new millennium. So I thought I'd just show you the process. This is what I showed you before. So this is the first time we moved from something which Gaudi had left specific information to actually being derived from the way that Gaudi works. So he never designed this window. It's something which we had to derive. We were using aeronautical software. So this is for the same software that was used to design the Boeing 777. We couldn't use architectural software. It's parametric. The entire model was driven by a spreadsheet. Because all these surfaces are mathematical, it meant that as designers, we end up working with numbers rather than with our fingers. This may seem odd, but you can judge the result yourselves. The stonemason was 1,200 kilometers away. He was in his late 70s himself. And I heard him on the telephone complaining to his colleagues back in Galicia that all they show me is spaghetti. Because in those days, that's 12 years ago, you couldn't do renders very easily. This kind of image was very hard to do in the time that you'd probably want to get it done. We found, though, that as the technology moved, we were able to start designing the pieces so that he would understand exactly what they looked like. And at exactly that same time, the first of the 3D printers arrived, and this is the wax model-making 3D printer. It cost $100,000, and each piece took 4 hours to make. We were very proud of these pieces. They were so incredibly accurate. Mr. Mayo, that's him there, thought we were complete idiots. He thought that it was much quicker to make his own prototypes out of polystyrene. It cost him nothing and took him only 2 hours. When he found out how much we paid for that machine to do this, for the rest of the time that we worked on the project, he always had one of these models either in his hand or in his pocket, just to remind us who was really the king. We had to invent new ways of describing the work. So that second question I asked, how do you communicate to the builders what they have to do? These are A0 templates. There are 780 for the window. They incorporate a render. This isn't the state-of-the-art now. This is the state-of-the-art 12 years ago, because I will show you what the state-of-the-art now is so you can make this comparison. We would give them these sheets. They had these coordinates on them. The only technology he had in his workshop was a steel wire with diamonds in it. And he invented this fantastic process whereby two people would be able to move this piece of stone while this wire came down. And then they would just finish it off. So everything had been cut by machine except for the last centimetre. When I asked this gentleman here whether he felt his life had been ruined, having spent all these years learning how to be a stonemason, he asked me if I was an idiot. Why did I think he would want to remove all the stone here when, after all we want to look at is the skill of the finish? So he was very happy that we could cut the stone to within a centimetre. I have a video just to quickly, I have to do it too quickly, I'm afraid, but it does sort of show the poetry of all this. So there's Mr. Mayo's office. Here's him interpreting the task that we had given him through this model. Showing it, that's the current director, Jordi Fauli, and Mr. Mayo on the left, again making use of his prototype. Then you see the piece of stone coming in. There's the template, has been marked on the stone. And then you can see the stone goes in, and this wire cuts it. And these gentlemen, as the wire moves, their job is to just keep twisting that stone until it gets to... So very, very clever work. And then you can see the big saw doing the flat cuts. And then finally... And he felt this was all he needed to do, and that gave him a lot of satisfaction. Still, we had to make the stones and prototypes at polystyrene at 1:1, so that the stonemasons could exactly cut. And then you can see the built with absolute millimeter tolerance. Because it was a parametric model, we were able to make adjustments to the measurements as we got nearer the thing. We have a 10 millimeter joint as tolerance. It turns out with Gaudi's system that he didn't need this at all. I've just spent a fabulous 2 days at the Argos in Cappadocia, where I saw immaculate masonry without any of these joints at all. So that question about whether Gaudi had ever been to Cappadocia, you can see that he hadn't, or certainly the team haven't, because we don't have the confidence to work without having that 10 millimeters of tolerance, whereas here in Turkey you can seem to work with no tolerance at all. And I congratulate you. Just to finish, I have 4 minutes, I believe. Correct? Yes? 3 minutes, that's enough. So just bring it into this decade. The story for this facade has, in fact, been a very interesting one. All we have to go on is this one drawing that Gaudi left. This is now just about to be finished, but I'll just show you the process very quickly. We're working with the artist Subarax to interpret these columns as a series of bones. You can see what happened before computers. This took 17 years to get the model to this point, but nobody accepted it as being the sort of, it doesn't have the magic of this. And we know that Gaudi was actually really keen on using these surfaces. So we set ourselves a challenge of how we could combine hyperbolic paraboloids, which are these surfaces here, with hyperboloids of revolution, which as designers, could we actually have a flexible plastic 4D model which would allow us to get exactly what we want. We want to get these intersections of straight lines, but not where they end up because of the geometry, but to get the geometry to get where we want it to be. This is the only drawing we do for the whole project. It's a schema. And that's the whole point of my talk, is that if you work in this way, you don't need drawings, you just need to have a schema. This schema goes from us to the mathematicians who did the simultaneous calculations to allow the programmers to build apps. So this is quite common now. You have an app within your software to allow you to go for the process. Parametric model, there's a lot to say about this, but no time to do that. Here are the prototypes that we made, and there is what such a column looks like. This has been made by Friedi Miller at a French boatyard in order for us to be able to test whether or not these columns were close to what Gaudi had intended. And you can just see that here. And then finally, in the 1 minute I have left, the process also, I think the future again, sort of picking up from Carlo's, he was talking about the multidisciplinarity of our endeavors. I think one of the future things is that we will need to work with the builders from day one. This is what this project has taught me, that if you work with people like Gaudí who's a third-generation stonemason, you can go through the process of understanding how you might make each piece so that it's affordable. We now cut the stone from the quarry to order. So these giant machines cut pieces of stone exactly the size we need. They're shaved with the diamond wire. You can see just how accurate it all is. And then Gaudí himself has set up a robot with 5 axes of movement and a turntable with 2 to make a 7-axis mill to cut the columns. We still have this a need for the hand labor, so it's a beautiful fusion of traditional and contemporary. It still takes a long time. Each of these core bits takes 45 minutes to make a removal of a piece of stone. There's the column as it's ready to go. It's 9.5 meters tall, just 3 pieces of stone. Gaudí, the stonemason, says we wouldn't be able to make this piece of stone so slender just by using hammers, so using the robot. The precision is extraordinary. Here's the column being built. It's everything fits perfectly. It's no straight lines. It's even a curved plan. So there you have, in 30 minutes, the entire history of Gaudi and the Sagrada Familia. I hope you can see that the changes that have happened in 20 years are an indicator of where we're going to be in the next 20 years. Thank you very much.
Mark Burry'e konuşması için teşekkür ediyoruz. If you want to take the questions.
Oh, great.
Yeah.
Apparently we have 5 minutes. Yep, sorry, apparently we have 5 minutes left for questions. Yep. Carlo. Carlo's got a question.
Hello? Yeah. Mark, thanks. That was really fascinating. Looking forward, these things and all this evolution, the past 20 years haven't been like the past 100 years. So I think from Gaudi, for a number of years, people kept on working in the same way. Evolution happens in big leaps and then it stops a bit. So I think we saw, from what I get it from you, what you said, we've seen incredible changes in the production, in fabrication, 3D printers or 5-axis machine and so on are part of the same family, and also in the modeling. What do you see as the next leap? Where do you think that will happen? So we've seen the 2 leaps you beautifully presented in both the modeling and the fabrication of stone or smaller models. What do you see as the next big challenge?
Thank you. The next step is this project here, which I haven't got time to talk about, but we have no information at all, but we're building an auditorium in there, which is based on this. The next step, I believe, is off-site fabrication in totality. At the Sagrada Familia, if you look at that construction of that great space here, everything you see here is made off-site. This makes sense. Even all the shuttering that's going on here has been made. Some of them are 25 meters long. But when it gets really radical is the stone. There is no stone laid on site. It is laid off-site. This site here is 5 hectares just outside Barcelona. It doesn't matter. What I was showing when I was certainly enjoying myself is a large auditorium on top of the building. It's 25 meters tall. And the images that I can't bring up, unfortunately, which Nope. The stonework, which you would imagine has to be done, and I mean the building is going. Here we are. Look. So I was trying to show you this here. This is the auditorium. This is the roof of the auditorium. Everything you're looking at is prefabricated off-site on a site that's 5 hectares in size. And you'd think, well, at least the stone would have to be laid by hand on site. But even that now is done off-site. So that's the shuttering that's underneath the concrete. And the stone that goes on the outside is actually laid at ground level and taken. Now, I think this, and at the moment I'm just finishing a book with my partner Jane on prototyping for architects. We've interviewed 50 architects around the world. Many architects are noticing now how much of the building of buildings will happen off-site, that you will bring it, and I think that is the future. And I think this building has actually got all that, that is already happening.
What do you think of the aim of the building? It's a building of belief, of faith, and etc. And what do you think about how the technology and all the facilities and the techniques we use in this time works really for architecture in a belief building and in high-rise buildings, and what's the difference in between them? Now we can build this and we can build and finish it in 20 years, and what do you think about it?
If I think I understand your question, I'm changing job next year. Next month I start a new job at a new university as Professor of Urban Futures. I'm asked, well, how do I reconcile this work, which is a large part of my life, with what I'm going to be doing? I say it's a bit like the space program. I happen to think that every city in the world ought to have a project like this that goes beyond the ego and the needs of one single, usually male, middle-aged architect, but actually transcends generations. So the fact there's only Barcelona doing it, I think is a pity. So every city could start thinking big. I think it's like the space program. There are so many lessons from this project. I've been working on it for 35 years. More or less my career has been showing the way forward for architects and construction because of this project. For the first few years I used to lecture and it was a kind of, well, this is like a medieval building, what's it got to do with today? I think it's the other way around. It's not about that we need to build these cathedrals or railway stations or sports halls, but we need to have these big buildings to ask the big questions so that we can then bring them through to the rest of the city, which of course ultimately is the housing.
Mark Burry'e konuşması için teşekkür ediyoruz.